Good morning, everyone. There is no doubt that combustion research is alive and well, as it's clearly evident by the massive attendance and support at this conference. Thank you. Peter Glaborg and I are pleased to report that for this 36th Combustion Symposium, you have achieved a new set of records. A record number of contributions first, with 1,315 papers submitted compared to 1,160 papers in San Francisco a couple of years ago. And as Professor Insuk told me this morning, we have 1,450 attendees as of this morning, which is also very close to the record number of San Francisco. Bringing this together was a huge effort that would not have occurred without the help of an entire team of people, and Peter and I have many to thank. First, the highly diligent office of the Combustion Institute, led by Bob Waranek, who's sitting there at the front, and her team. Their professionalism is unparalleled. They are a well-oiled machine that works like a clock, so thank you, Bob and your team. The president of the Combustion Institute and the various committees as well for their wisdom and generosity. So thank you again. The Program Advisory Panel and the Publication Committee, whose advice was extremely valuable in establishing the framework of the program for this week. So thank you. And many other colleagues who shall remain nameless have also been generous to us with advice and have put up with our continued pestering. So thanks to all. A key feature of the program is the industry perspective sessions, which are held at 3:20 every day except Wednesday. Highly experienced professionals from a broad range of industries have kindly volunteered their time this week to bring together a closer interaction with their fields. Please make the time this week to attend these sessions, but more importantly, to interact with these representatives who will be available throughout the week. Their names and photos will roll on the screen, so you will be able to see them and recognize them. I also would have liked to thank, and I missed that, 65 colloquium co-chairs whose dedication and hard work through tight deadlines has led to the high quality program that we hope you will enjoy this week. The names of these co-chairs are supposed to be rolling in the screen, I guess, and if it hasn't yet happened, it will probably happen in the next few minutes. We hope that you enjoy the program, both technically and socially, and we hope that you benefit from the state-of-the-art research that will be presented throughout the week. To kick it off, we are pleased to introduce Professor Thierry Poinsot as Hottel Lecturer for the 36th Combustion Symposium. Professor Poinsot is a research director at CNRS, head of the CFD group at Surfax, senior research fellow at Stanford University, and consultant of various companies. He has received his PhD in heat transfer from l'École Centrale in 1983 and his thèse d'état in combustion in 1987. He then postdoced for 2 years or so at Stanford before joining Surfax in 1992, where he currently leads a massive group of researchers, some 60 of them I've heard. He is a world leader in numerical combustion, and he performs direct and highly relevant applications, numerical simulations in applications to practical problems. He has co-authored more than a couple of hundred papers in various journals, and he has received many awards, including the Grand Prix of the French Academy in 2003 and the Aeronautics Prize of the Association of Aeronautics and Astronautics in France in 2014. He has an elegant and informative teaching style, which I'm sure you will appreciate as he's delivering his 2016 Hottel Lecture on the prediction and control of combustion instabilities in real engines. Please make him feel welcome.
So, thank you very much. Assad and Peter for this introduction, and thank you also for inviting me today to give this lecture on combustion instabilities in real engines. It's an interesting coincidence, actually, that we have this bell here, because in the same way that a hammer was used to ring this bell, I'm going to show you that flame can be used to ring a combustion chamber. But unfortunately, the consequences are not as pleasant as here. The outline of the talk is the following. So is this thing going to work? Let me see. I will start by a brief introduction on combustion instabilities in general before discussing engines. What I mean by engines is here that I will split basically combustion chambers into two categories. The combustion chambers that you can operate in the lab, so basically I would say reasonably small, and the combustion chambers that you cannot operate in the lab because they are real engines and they are too powerful. Then I will take two examples, gas turbines and rockets. My objective here will be to show you that for these two applications, combustion instabilities are a major problem and they need to be studied in a different way compared to what we've been done before. So let me begin by combustion instabilities. Instabilities are basically everywhere in combustion. Even for the simplest problem of making a small spherical flame, laminar one, very rapidly, instead of having a smooth surface, you end up having wrinkles everywhere, cells, and all these cells are going to make our life very complicated because this device, for example, is used to measure flame speeds. Right away, you see that even at the smaller scale, you have instability problems. If you go to large scales now, you also have instabilities. If you try to do a pool fire, you're going to see these big puffs, for example, which are due to the coupling between combustion and buoyancy. Now, sometimes instabilities are useful. If you want to atomize, for example, a liquid jet of fuel, it's very useful to have instabilities at the liquid-gas interface, and we rely actually on this instability to produce the droplets, which we will later burn. There will be a lot of acoustics today, so you see it's already happening. So now, among all the instabilities in this combustion world, one of them is unpleasant, and it's subacoustic instabilities. Why? Well, because they basically break engines. I will show you that today. And these instabilities are due to a coupling now between acoustics, like this one here, and combustion. There's been quite a few very good review papers and books, including here plenary lectures at the Symposium, and my objective is not to repeat them. I just need, for a few minutes now, to introduce the basic mechanisms which lead to subacoustic instabilities. So the first one is the fact that flames produce acoustic waves. And there will be a few equations today, not many, but I would just want to focus on that one for the moment. If you have in a flame unsteady heat release, then it's quite easy to show that in the far field of a flame like this one, you're going to have sound. Okay, so a steady flame does not make noise, but if a flame starts moving, it will make noise. It's beautifully illustrated on this movie here, where you have a Bunsen flame which is pulsated here and which oscillates, and you see that every time you have a change in flame surface, so every time you have a change in heat release, you make these huge acoustic waves here, which are visualized here by the divergence of the velocity. So that's one part of the problem. The other part of the problem is that flames are also very sensitive to acoustic waves. If you send, for example, here, acoustic waves onto a flame, this is again a simple Bunsen flame, you have this kind of behavior. Well, you can see how the flame here is modulated by the sound that you send here. You don't have to send only harmonic waves, you can also send music if you want, the result will be the same. You see how the flame reacts to that. Now, if flames are influenced by acoustics, and if flames influence acoustics, then there's this possibility that you can have a resonant loop between these two phenomena if certain criteria of phase and gain are satisfied. It's not always happening, but when it does, the level of noise increases, and then you end up with these kind of things here. By the way, you see the main problem of people working on this field is that they become deaf after a short time. And you see how unpleasant it is. Now, this is a small engine. It's not an engine, actually. It's a lab-scale experiment, which is built to resist. If this happens in a real engine, then you have a major problem. Now, this is another view of another experiment. That's the 80s, the experiment of Berkeley, where you have a flame stabilized behind the backward-facing step. And you see that for this case here, you have a very strong unstable mode where the flame flashes back into the inlet. And we now know more or less the mechanisms here. The mechanism is the following. You create a large vortex. This vortex will burn. When it will burn, it will produce acoustics, as I've said at the beginning of this talk. These acoustic waves will create a new change of the flow rate here, which will create a new vortex. And in certain conditions, this thing basically gets self-amplified. Note that in a system like this, at certain instance here, the velocity becomes negative. That's why the flame is actually flashing back. So it's a combustor where the flow exits the combustor by the inlet. And I think everyone understands that it's a bad idea. Now, if this thing wants to move, why do we need to discuss real engines? Well, it's because we need to move away from this, I would say, lab-scale systems to this kind of engines. Because in this engine, if we have a combustion instability, it's not an interesting research problem anymore. It's a major problem. It's a major risk in terms of the program itself. So this is why we need to discuss this kind of problem. The most famous example of big problem related to instability is the Apollo program and the F1 engine. The F1 engine was built from a smaller engine. It was upscaled, and then it became unstable. And there's a very nice paper by Offelan and Young here which summarizes all the methodology which was used at the time to try to fix the problem. To make it short, what you have to remember is that those guys had to do more than 1,000 full engine tests. That's not a lab scale, okay, it's the real engine, to try to find a way to fix the problem. The way to fix the problem was to change the injectors. Let me go back here. Change the injectors, add some baffles here to damp the acoustic waves. And the way they did it was basically by trial and error. So it lasted 2 years, and the cost was amazing. So this is why here, some acoustic combustion instabilities are not just a curiosity and an interesting fundamental problem for the combustion community. They are a major risk. And today, the situation has not changed. If you build a new engine, you have to face combustion instabilities at some point. Now, my objectives today are to present quite a few examples of instabilities in real engines. I will also describe results obtained in lab-scale experiments when they are relevant for real engines. And I will use 3 methods to do that: experiments, LES, large eddy simulation, and theory. Experiments, that's an interesting problem right away. If you do experiments in the lab, you know that today we have methods to measure full 2D, even 3D fields of species, radicals, flame position, velocity, and of course pressure. If you go to a real engine, well, usually you don't have that. In most cases, what you have is that this engine makes noise, or it vibrates too much, or it's just exploded, and we don't know why. And in the best case, you're going to have maybe pressure measurements, microphones. But that's all you have. You don't know what's going on inside. So you're basically blind as far as it goes to the problem of what are the unsteady phenomena in this engine. So here you need something to put your eyes inside the engine, and this is where the LES comes into the picture. LES is a way to create a virtual burner. In that case, we'll be able to use LES to probe what's going on inside the burner. And the LES revolution, maybe I would say 10 years ago, has allowed us to build things which look, they are not exact of course, but they look like the real engine, and they capture most of the unsteady activity in the engine so that we can actually use them to try to understand what's going on. So it's actually interesting to see that many companies in the industry have moved or trying to move today to LES, not to compute the mean flow or not to compute the pollutants, but usually the first motivation is because they are afraid of combustion instabilities. And they know that the best method to try to control that is LES. Of course, this is only possible today if you have massively parallel computations. And most of the simulations I'm going to show today are typically requiring thousands of CPU years. So it's not cheap, but compared to a real engine, it's still not that much money. So the third method I wanted to mention here is theory, and I will insist today, and I would like to convey this message to the young people in the room. You might think that if you have all these nice computers and all these big lasers, we don't need theory. And actually, what I want to prove today, by multiple examples, is that we need more people doing theory in the combustion community. So just, you know, a pen and a paper, and we don't have enough people doing that anymore. We used to have many theoreticians in this community, and we don't have enough today. And I will give examples of that. So let me move now to the description of what real engines are. And I will basically try to illustrate that by comparing real engines to lab-scale experiments. So what is different if you try to study a full engine? The first thing, of course, is that the Reynolds number and the Damköhler number are going to be much larger in a real engine because they're just more powerful and larger. That's an obvious difference. But in terms of modeling, it raises questions for us. The second difference is that the shapes of these chambers are different. This is an example here of a lab-scale experiment, which we call the Volvo rig in this community. And it's a rather simple experiment, but the geometry at least is simple. It's a long tube with a triangular flame holder here. And the flow there may be complicated. This is a LES actually of this flow. The flow may be complicated, but the geometry is simple. Okay? Now, if you go to a real engine, it's a different problem. Now, the geometry is going to be complicated. Of course, then we expect the flow to be even more complicated. That's for a gas turbine. If you go to a rocket engine, it's a bit different. In a rocket engine, the elementary piece here is a coaxial jet, where you inject usually one reactant in the middle, and around it you supply the second reactant. So that's a simple geometry. But unfortunately, you have too many of them. In an engine like the Vulcan engine, you have 566 injectors. So that makes, of course, your life much more complicated. Now, another difference, it's the regimes of combustion. I know that in this room, basically people are split into two categories, those working on diffusion flames on the right side and those working on premixed flames on the other side. They even have the separate workshops usually. In an engine, it's not working like this. I mean, we don't have premixed engines and diffusion engines. And actually, if you look at a gas turbine like this one, and you do an LES of this thing, you find out that you have premixed flamelets at certain points, and diffusion flames at another one in the same flow. So we right away guess that most formulations, most models that we use are not going to work when we're going to try to apply them in a full engine. Okay? So that makes things a little bit more complicated again than what we can do in the lab. Now, another difference now is different instability modes. I will talk here about two categories of modes, hydrodynamic modes, vortices if you want, and acoustic modes. So let me start with hydrodynamic modes. We know, and we have seen that for a long time, that in many thermoacoustic phenomena, vortices play a big role. That was indicated even a long time ago. This is the book of Reinst, if this thing works, okay. Reinst was working on unsteady combustion before the Second World War, and even at that time he was plotting things like this and saying, if you create a vortex like that in a chamber, you have a big danger of going into some kind of thermoacoustic mode. Actually, these vortices, this type of vortices here, we saw them a bit later. That's an old paper now, it's an 86 paper, which is showing vortices created in a premixed chamber, and you see, you recognize exactly this shape here. So that tells us right away that the way the flow can organize itself into structures, into coherent structures, is important for thermoacoustics. Now, how do you study that? Well, people who do non-reacting flows have looked at that for a long time. It's called linear stability analysis. And I'm going to take here one example of such flow taken by famous people here. Mankiewicz, you know, with UR, was one of the specialists of these studies. And you look, for example, at the flow behind the triangle here, behind the flame holder. The velocity profile will look like this, and the temperature profile will look like that. So this is cold, TU. This is hot gases, TB. And you can write theory to look at how unstable this flow is going to be. And this will depend on the ratio TB over TU, actually, the temperature ratio. When you do that, and if you start by looking at a case where TB over TU is unity, so it's a cold flow, what you have is a sinuous mode. So the flow will organize itself to have this kind of movement. But if TB over TU is larger, actually this movement completely disappears and you have a varicose mode now, which is very different. And of course, you expect that in this case or in that case, we're going to have very different acoustic modes after that. Now, interestingly, we should wonder now what is the ratio TB over TU in practical cases. If you look at lab scale experiments, you know that in most cases we use cold air. We don't like to heat up the air, it costs a lot. So we use TU equal 300K. So TB will be of the order of 2000. So TB over TU will be like 6 to 8. But if you look at a real engine, it's different because here we compress the air, 700K or 800K, and usually we can have also lean flame. So TB over TU can be anywhere between 1.3 and 3 maybe, 1.5 to 3. So it really means that in the cold flow we have a sinus mode, in the lab scale we have obviously a varicose mode, and the real engines are somewhere in between. And this problem was studied by Emerson and Lewin a few years ago, and actually showed that for TB over TU equal 2.4 here, you have something like a varicose mode. But if you go to TB over TU equal 1.7, you have a sinuous mode, which, by the way, tells us that if we want to study real engines in the lab, well, we have to use the same temperature ratio. Otherwise, we're going to miss a very important aspect, because this is not going to trigger the same instabilities as the varicose mode. Another big difference is now related to acoustic modes. If you look at the literature on acoustics, you're going to find out that 95% of it is dedicated to low-frequency longitudinal waves, where the acoustic waves interacting with the flames are actually propagating in the same direction as the flow. Okay? If the flow is going that way, the waves are going upstream or downstream. And there are many examples here. I just picked up again the Volvo rig. That's a view of the experiment. You can see these big vortices created here. That's an LES, and that's the usual problem. And this is what we do usually in the lab. Now, the problem is that in many cases, especially in real engines, you also have transverse modes. So what is a transverse mode? It's the same thing, except that now the waves are traveling in the other direction. So instead of going in this direction, the acoustic waves actually propagate in this direction. And when they do that, they are usually a higher frequency of the order of 4,000 hertz, for example, in that case, in the paper of Rogers and Marble. Those waves have another characteristics, and it's that they are much more dangerous. If you trigger a high-frequency instability in an engine, usually you end up with an explosion after a few seconds. I picked up here a sentence by this company, Copenhagen Suborbitals here, telling you how much we know, how much we understand, and how we try to fix those problems. Okay, the recommendation of those guys is this one. Okay, this is, if you want to fix this problem, you need to pray. That's, and if you are managing a big industrial program, you realize that this will make you nervous. Okay, next step, of course, will be to say we need to understand what's going on in the real engine. Can we just take a piece of it to capture the instability modes, to try to, to study it in the lab? Unfortunately, that does not work. What you would like to do is to take, for example, this is a gas turbine combustion chamber. You would like to pick up one injector, put it in the lab, and just study one at a time. Same thing for rocket engine. You would like to pick up one injector and just study this one. But that does not work because the acoustics will be different. And this was tested actually by Croco a long time ago. He took a rocket engine and tried to block part of it. And what he proved was that every time you change the engine, you have a different unstable mode, even if you keep the same injector. So you need the full engine if you want to capture some acoustics. It's certainly not true if you want to do only mean flow studies, but for combustion instabilities, it's required. Next difference is boundary conditions, and that's also a big one. If you look at what I've just said here, I've told you that a lot of things were controlled by acoustics, which really means you need to know if a wave is leaving the combustion chamber, how much is going to come back. Okay? So that's called the reflection coefficient. It's an acoustic notion, of course. You have to do that at the outlet and at the inlet. And in laboratory cases, it's kind of easy to do that. In many cases, we impose here that the flow is blowing into the atmosphere, and we know that pressure is imposed, which is fully reflecting. And at the inlet, normally, if you get a serious experimentalist, he has a choke nozzle, so you know that the flow rate is imposed. But in an engine, in a real engine, things are different. In front of the chamber, you have the compressors. And after the chamber, you get the turbine. So the chamber now is surrounded by strange elements. On one side, you have the compressor, on the other side, you have the turbine, and you need to know if waves propagate in this direction, how much is coming back. Same thing on that side. Otherwise, you cannot study the instability of this engine. And so you need the reflection coefficients there. And that, of course, is not a combustion problem. Now it becomes a turbomachinery problem. You need to be able to do this kind of simulation where you send a wave into a stage here of a turbomachine and see how much is coming back. So in itself, that is a very, very complicated problem, which is not combustion, but you need it. Okay, I added this slide actually yesterday night because I know how many chemists would be in this room. So I would just like to add also that our knowledge of chemistry in this engine is very, very insufficient. So that's a message now to the chemists. I think everyone in this room will certainly argue about the flame speed of a methane air flame at 300 K and 1 bar, okay? I think Fauquion will tell me it's 36 centimeters per second. Others will tell me it's 38 or something. But I don't really care about that. I would like you to tell me what's the flame speed of this thing at 20 bars, 800 K, and an occurrence ratio of 0.5. Well, we don't have the answer to that in an experiment. No one does these experiments. And if you run the usual full chemistry schemes here, the error is not a few centimeters per second. The error is more like 200%. So if you want to do the LES with that, you don't know what to do, basically. We don't know enough about chemistry here. And if you go to a rocket engine, it's even worse. If you go to 120 bars, well, depending on the scheme you use, you can have flame speed varying between 20 and 40 meters per second. So that's a big problem, because, of course, if we want to use LES, well, we need good schemes. If we don't have the chemistry, we cannot do anything. So that's a major problem, too. Okay, let me move now to the next point, which is gas turbines. So you find gas turbines in many places. I want to describe a little bit the configurations here. And I'm going to do that using a result of a joint study between Surfax, EM2C, and Cambridge and TNU. So just to remind you of how a gas turbine works, we basically have the combustion chamber here. The air comes from the compressor, goes to the turbine here. We inject the kerosene in different places here. It can be also methane. And we have sectors here. Each sector corresponds to one injection here of kerosene. And in the given chamber, you can have 10 to 24 injectors. This is a cut for an helicopter chamber, which is a little bit more complicated because it's more compact. You inject the air from that side, goes into the chamber here, flows into this zone here going to the turbine. And here you have a swirler here, which is here to mix the kerosene with the air. A specific point about gas turbines is that they have this annular shape, okay? And if they have an annular shape, now it's allowed for acoustics to follow this path. So an acoustic wave can actually travel all around this chamber, which means that we can have an acoustic mode, and the first mode frequency can be obtained easily here just by dividing the sound speed in the chamber, which is of the order of 700 meters per second, by the perimeter of this chamber. So this number is usually of the order of 1,600 to 1,000 hertz. Actually, this mode is degenerate because there can be two modes. It can be turning in the clockwise direction or in the counterclockwise direction. I'm going to introduce here a very simple model. There are not many equations today for the moment, which are called the SLIM model, the simplest linear model that you can have for the pressure perturbation. If you assume that the propagation is one-dimensional, you can write P prime, the pressure perturbation, at a given angle and a given time as this function here. Since this is a linear problem, the general solution is the superposition of the two solutions here, the wave turning this way and the wave turning the other way. To give you an example here, this is a case where A minus is 0, and you see that what you have is a rotating mode, so that when we plot now the modulus of the perturbations here, or the phase, the modulus is constant because every point here has the same perturbation, And the phase is just unwrapping exactly like the angle because it's turning all along the azimuthal direction. This is A minus equals 0. If I take A plus equal A minus, we have now a standing mode. You can recognize here pressure nodes, which are here and here. And the phase now is opposite. This point is oscillating in an opposite way to that one. And if you have A plus and A minus different, you will have what we call a mixed mode where the shape can be anything of that type. In real chambers, what's interesting is that we find both standing and rotating modes. We don't really know why. We have quite a few indications. We believe that it's probably due to the amplitude of the instability or to the shape of the chamber, if it is perfectly axisymmetric or not. And the modes also can oscillate between standing and rotating in the same machine over time. So you can have a standing mode in this machine, you come back 1 second later, and then it will be turning. Field measurements were done by Siemens, actually, more than 10 years ago. They took a big turbine, a real one, and they installed 12 microphones on it, and they measured the sound field. And this is the results they obtained. Just remember that to get that, you need 12 microphones and a gas turbine. Okay? So it's an expensive experiment. So this is the result of Siemens plotted as a function of the angular position. Here you have the modulus, here you have the phase. And when you superimpose the slim model on it, you find that the slim model works extremely well here, telling us that at this moment, in this chamber, they had a standing mode. Interestingly, they also made measurements a few minutes later, and then they had these measurements, which corresponds much better to a standing mode. So you can have in the same chamber a turning mode or a standing mode, and Siemens was actually the first to demonstrate that. Now, a few years later, other groups started looking at azimuthal modes, building annular chambers now in the lab, which is difficult, but you can do it. For example, Cambridge had this chamber here where you can look at the flame from the outlet here and look, for example, at the unsteady reaction rate in this chamber. So now you have here the unsteady reaction rate. You take the local reaction rate, you subtract the mean, and you see that now, obviously, what we have is a counterclockwise mode turning in this chamber. Cambridge did actually something more. They measured the amplitude of A plus and A minus and plotted the probability density function here of the two. And you see that for this chamber over time, you have two possible states. Either you have A plus equal A minus, which tells you that you have a standing mode at this instant, or you have A plus non-zero and A minus close to 0, which tells you that the mode is probably spinning. And you see that there's a probability that the flame will go from one to the other, and we believe this is due to turbulent forcing. Now, École Centrale then also did an experiment, but then they had transparent walls, so you can see what's going on inside the chamber, and you can also hear it. So that's a view of a low-frequency mode. Let me show you now an azimuthal mode here. And again, you see how unpleasant it is. So we start having now a few experiments where we can look at azimuthal modes. Interestingly, we actually did the LES before we did the experiments here. The reason for that is that there was a French engine which had problems maybe 10 years ago. We thought they were due to thermoacoustic problems, and so we were asked to do a simulation of the full engine. At that time, it was quite difficult, so we said, okay, let's try to do that. We took one sector, we did an LES of this sector, and then we copied it 14 times, as you can see here, and we restarted the simulation now on a big parallel machine and just waited. And what's happening in this engine is that over time you see that you start developing an unstable mode here. And when this mode grows and reaches a limit cycle with about the same frequency and the same amplitude found in the real engine. So that was a very interesting result because it's telling us that yes, you can capture a mode like this with LES. And if you do now, you can interrogate this simulation to try to see what's going on. So you recognize here that there is certainly an azimuthal mode, and you see how the flames are actually dancing now in this azimuthal mode. If we zoom on this movie, you can see here the flames oscillating in the acoustic field, but more importantly, if you look at this zone here, you will see that there is also flashback. The flames enter the swirler, and then they are ejected again. So you can, again, measure now the pressure oscillations versus the angle, and compare it again to the slim model. And you see that you can match the LES here with this very simple model with A plus equal 1, A minus equal 0.96. So there's a message behind that, is that even in this complex flow, complex turbine, the acoustic structure itself is very simple. You can predict it with this very simple model. There's another message behind it, actually. It's that this mode is really close to a standing mode. Even so, your eyes seem to tell you that it is turning. It's actually close to standing because it's close to A plus equal A minus. Then you can use methods like POD or DMD, which I don't want to describe here. You can take a look at this paper here to extract this mode, and this is what you obtain. This is the most intense mode in this chamber, and it is a standing mode where you have pressure nodes here and there and pressure and time nodes here. So I'm not going to continue along that path because my message at that point is the following. You can do LES here, and we've done it, and you can do experiments of this engine, and they just tell you, yes, there is a problem. You have an unstable mode. Now, if you want to fix the problem, you cannot repeat this LES all the time. So you have to find another way. This is where we need to go to reduced order models or to theory. We need to do something more to be faster. So if we want to talk about reduced order models now, we have to recognize that everything in this problem, almost everything, is controlled by acoustics. And so we could try to solve this problem only by solving the acoustic field and replacing the flames by some kind of loudspeakers. And the way to do that has been actually touched by many people in the last 10 years. And I think a lot of people see the potential of these methods now, which are needed in addition to LES and experiments. So what you do, you replace this very complicated geometry. You recognize that not all details are important. You can say that, for example, this annular chamber is like a circle here where waves propagate in one dimension, and the chamber here of combustion are replaced by small ducts, 1D ducts. And the flames here are the only critical problem. Well, you replace the flame using what we call flame transfer functions introduced by Croco more than 50 years ago. And Croco said, if you can relate the unsteady reaction rate in the chamber to the unsteady velocity at the inlet, then you can close the acoustic problem. And this is what we use in most of these methods. And you can recognize here that the transfer function between these two has an interaction index, n, and if the interaction index is close to 0, there is no problem, your flame will be stable. And tau is the delay here. Tau is the time it takes for the burner to react to a pulsation at the inlet. How do you measure flame transfer functions? You can measure them experimentally, or you can compute them. This is an example for a Bunsen flame here, where you pulsate the inlet with a sinus waves, and you measure the Q prime, the oscillations of reaction rate. Now you have two sinusoidal waves, you can deduce the phase and the gain very easily. Once you do that, you can close completely your equation. For the burner we're studying here, for the helicopter engine, we measured tau here, and it's of the order of 0.7 milliseconds, which tells us that in this engine, when you change something at the inlet, it takes about 0.7 milliseconds before the engine starts reacting. Now, we developed a method which is called Atacama. Here, I will just keep this name to refer to it. It's going to be faster, which solves all these equations and provides a fully analytical solution. And what the fully analytical solution tells you is that it gives you the numbers, the physical numbers, which actually control this flow. They are called the coupling parameters, gamma I. These coupling parameters, gamma I, can be written as a function of the flame transfer function and of the sound speed, the cross sections of the different burners, and the length of the burners. So it's something fully analytical. You can just derive it by hand. Once you have these numbers, you can have the frequency of the mode. You recognize here that the frequency of the modes which will appear now with combustion is the frequency that you have without active flame, and there's an additional correction here, sigma, and this term sigma is just the sum of all the interaction indices. So again, you have a fully explicit solution, and you just have to take the real part of that to have the frequency of oscillation, and the imaginary part will be the growth rate. If the imaginary part is positive, you're in trouble. You have an unstable mode. If it's negative, you're fine. You have no problem of instability. You can do that for the burner I've shown you, for the helicopter chamber, and this is the result of the theoretical method here. You have here the time delay, and here you have two zones, the stable zone and the unstable zone. And you see that the theory tells you that if the delay is more than 0.6 milliseconds, then the engine will be unstable. But if it's less than that, it will be stable. And the LES we did was actually exactly here, so it was indeed unstable. And that confirms the fact that LES and theory agree here. But now theory gives us another very important result. Theory says, well, you just have to move your delay a little bit here and the engine will become stable. So that's what we did. We went to the LES and we just decreased the delay by making the flame a little bit faster. And then we got to the point where the flame, actually, you can see time here, you can see the pressure. You see with the standard flame, the oscillations here, and you see that when we went to this modified flame, the oscillations died really fast. And actually, if you look at a movie of what's going on here, when we change the chemistry, you see here these very large oscillations, and you see that they are damped, and now they are completely gone. So you see how we can combine now theory and LES to try to understand how to control these flows. It's not the only thing you can do, actually. I want to take now another example and another analogy. You know that if you walk on a bridge, it's probably not a good idea to have people walking at the same pace because you're going to excite the structure modes in the bridge. It's actually forbidden in certain bridges to do that. It's the same in an engine. Why do we use all similar burners? It doesn't look like a good idea. We should use different burners. All of them could be different. Today, I want to do only one case, which is the case where we have only two types of burner, which I will call the burners of type 1 and burners of type 2. Why do I use this case? Well, because in practice, this has already been done by Siemens. Siemens takes standard burners and they add some metal extension here so that these burners have different flame transfer functions. So in practice, you can call those type 2 and those type 1. Okay? So now the question is, can we mix those things in such a way that we have better stability? The problem is that there are so many ways to do that. You're not going to try all of them experimentally or numerically. You need a guideline. And this is where theory comes into the picture, because theory can help you to do that. Theory tells you that now, since you have two types of burners, you're going to have two gamma I's, two interaction indices for this type of burners. And theory gives you actually the form of the modes. This is the result of the theoretical approach here. You recognize what we had before. This is the mode you obtain when you have identical burners. And now that the burners are different, you have a correction here, which is called S, the splitting strength. And the splitting strength makes these two modes different now. They don't have the same growth rate. They don't have the same frequency. And once you have the theory to guide you, you can apply it, for example, to do the following test case. Suppose you have a chamber where you want to place 4 burners of type 2 and keep 20 burners of type 1. And suppose also that for practical reasons, you want to group them 2 by 2. Now you have only one parameter to choose. What is the angle that you want to choose between these two things here? Well, you can run the theory, and theory tells you that the best arrangement, the most stable one, is this one. Okay. So there's no need to try all of them. At least you have an idea that this should be the best one. Then you can go to LES or to experiments, and you have a way to avoid trying to test all possibilities, which would be impossible anyway. Okay, let me continue now with the rockets. Now, this is a joint study also between different groups in Europe. Surfax and IMFT in Toulouse, EM2C in Paris, DLR in Germany, Onera, and TU Munich. The problem is rocket engines, of course, is that the power density is so large that when anything starts going wrong, then you kill the engine very fast. Okay? And this is not what you want to do, of course. So you need to find a way to understand what's going on in these engines. Doing experiments, obviously, is difficult. Okay? If you want to study this engine, bring it into the lab, it's going to be crazy. And this is the argument we use quite often to say, okay, let's do a simulation. But the problem is that simulations are also very difficult. Why? Well, because the flow in these rocket engines are a little bit tough. Not the injector itself. The injectors are simple. Those are the coaxial jets I've shown you before. But the thermodynamic conditions are complicated. Why is it so? Well, if you look now at a PET diagram here and an injector here where you inject nitrogen here, you see that if you are at low pressure, you basically go from this point here to that point here, which takes you here in the PET diagram. And so basically what you have is a spray because you cross the boiling line here. And so you atomize your spray. That's what you expect to do. But when you go to high pressure, it's different. Now you can go from this point here to that point here without ever crossing the lines here. and the boiling line. So which really means that what you have now is a transition between a dense fluid to a light fluid. And you can do that in an LES, but there are many problems here. The first thing is that you have to forget about the state equation. The perfect gas equation has to go away. You need another equation, but that's not the worst problem. You can do that. The worst problem is really that in this flow now, you have one fluid with a density ratio which is more than 500. And numerically, this is very difficult to do. People do it. That's an example here of a simulation of endodecane injected into nitrogen, 60 bars. And you see that, well, you can handle the problem, but basically you need to rewrite your code. And you see here what we call the liquid core, but remember it's not the liquid and here the gas, it's all the same phase actually, it's all the same fluid. You can add combustion. For example, here if you look now at a case where you have combustion, you have here liquid oxygen and gaseous hydrogen on the other side. And you can do a simulation of that with reaction. And again, I'm not going to follow this path because when you do that, you never find any instability. Okay? It's always, thermoacoustically speaking, these things are always stable. And we know now why. We know that this is due to the fact that to capture instabilities in a rocket engine, you need multiple injectors. So what means multiple? Well, more than one. But in the real engine, you have 500. So you have to stop somewhere. Onera, for example, tried a 5-injector system. And EM2C computed it. That's an example of result here. But you see that when you compute this thing, it's, again, fully stable. So you need more than 5. Okay? Well, the problem is that when you add injectors, the power goes up very rapidly. And remember, those are 80 bars experiments. So it's not a cheap game here. So you need to increase the number of injectors. Well, that's what DLR did. DLR went to 42 here. To go to 42 injectors, they had to make them smaller. But even like this, the power of what I'm going to show you is 100 megawatt. So I'm not sure we can really call it a lab scale experiment. Okay? It's not something you would do in a university that easily. Also because now the scales are smaller, the frequencies are going to be higher. You're going to see numbers of the order of 10 kilohertz just because they had to scale down this engine. So this is how the engine looks like. So this is oxygen, hydrogen. So right away, you guess it's going to be dangerous. You have to do that in Germany, and you have to be careful. But even in Germany, I think they are afraid of this animal. So you have a nozzle here. You inject the H2, O2, and with this dome here, you're able to mix them with these 42 injectors. Each injector looks like this. You have the liquid oxygen here, and the hydrogen is injected there. Now, the database which was gathered by DLR is a big one, of course. I just wanted to take 2 cases to show you that we can indeed, with LES today, explain what's going on in the engine and capture these activities. So we picked up 2 cases. One will be called low power, and it's what we call a stable case. The other one is unstable, and it's a high power case. Now you have to understand that when these guys say stable and unstable, they really mean stable, maybe we could use this engine. Unstable, it would explode, okay? Because here, the unsteady pressure will be of the order of 40 bars peak to peak, and the mean pressure may be 80. So you can imagine the structure, if you have a 40 bar oscillation, it's not going to survive for a very long time. I would even say it's not going to survive at all. So we picked up these 2 cases, and what was interesting here was to look at these 2 modes here. You can see these 2 monsters here, big modes, and DLR actually insists, and I understand why, they insist on understanding where these modes come from. It's not only the fact that you say they are there, you have to tell where they come from so that you can find a way to mitigate them, to kill them. So we did an LES, and again, that was a big game here. You can see the 80 million hours needed to do this computation. And this is the result of the LES. Here you can see the temperature field. You can see all the injectors here and the flows through the nozzle. And when this LES was done, it took, a few months. And then after that, the result was, what about instabilities? Again, remember, we are looking for instabilities. Well, there was no instability. So people gathered and thought about it, and we saw 2 possible explanations. The first one we did not like was that the code was not good enough, okay? That it was dissipative, and that it had a problem with the mesh density. So we checked the mesh independency. we found that the results did not change with the mesh, so we thought we should investigate another explanation. The other explanation is that maybe these oscillations are not linear. They need some push, they need some triggering to begin. You know, there are many systems which work like this. They are non-linearly unstable. You need to push them. And so this is the explanation that we try to investigate by adding a perturbation on the flow. So this was done in the following way. We knew from DLR that the mode which appears in this system is usually a transverse mode, so we added the transverse mode at one instant, and only at one instant. We don't do that over time. We take the flow, we stop it, we add this perturbation, and then we let it go. And we scaled this forcing by the mean pressure, and we went from 3% to 13%. So when we do that, we obtain the following results. When we try to force at low amplitude, the low power case, we added some perturbation, but then they died right away. And same thing for the high power case. So we said, okay, we need more power maybe, so we went to 6%. And for 6% was the same actually. When we force the system, it goes back to stability. But then finally, when we went to 13%, this one was going back to stability, but this one was not. And here, we saw that we had a self-amplified mode, and this one does not die then. After that, it keeps going forever. So it's really telling us that we can, in this LES, create a self-sustained oscillation. And that's what we were looking for. So now we can analyze this oscillation. Again, because now we can look into everything because we have the full LES fields here. It's a big database, but you can look into it. So that's a view of the pressure now on the skin of the engine and on a cut here, which is located in the chamber. And here you have the temperature field. Look here at the pressure signal somewhere in the chamber. You have 40 bars, peak to peak. So this is the right order of magnitude, and it's a very strong, unstable mode. Look at the temperature field here. You can see the flames dancing in the acoustic mode, but remember that they are also the source of the acoustic mode. Okay? It's a self-amplified mode now. This thing would keep oscillating forever. Now, if you look now at the comparison of the pressure spectra obtained with the LES and obtained with the experiment, you see there's a very good match. It's actually even surprising. The mode 1 obtained in the experiment is captured really well in the LES, and the mode 2 is also captured very well. Mode 2 was actually called mode X by DLR at that time because they were not quite sure of the nature of that mode, and you're going to see here that with LES we can actually explain where this mode comes from. So what we did, you need to take quite a few of these snapshots here, maybe 1,000 of them, and you do DMD again on this thing, and you can isolate the modes. So for example, this is mode 1 only. And you see that mode 1 only is a transverse mode in the chamber between these two walls here, and a longitudinal mode 3.5 actually in the dome here, in these lines here. And it's a coupled mode, okay? It goes together. So we can really identify this mode, and the frequency is the right one, the one observed in the experiment. And then we can also capture the second mode. And the second mode is actually a radial mode. It does not have a dependence on the angle. It's located really here in the chamber, in this zone. And this mode now is again a coupled mode where you have a transverse mode in the chamber, a radial mode in the chamber, and a longitudinal mode in the dome, but higher order. So again, it shows here that if you combine now the LES and the experiment, you can isolate things which are happening in the real engine. And if you want to know more about that, there's a paper tomorrow which will give much more information on this problem. Okay, I'm almost done. I just want to finish with one thing, which is an anecdote, I would say, or a short story about something which is called intrinsic instabilities. If you followed my talk, you will have recognized that I have designated reflection, acoustic reflection, as the most important and the guilty phenomenon in all this business. In other words, I've told you, if waves are reflected at the outlet or at the inlet, we can have combustion instabilities. That really tells you that one way to mitigate these instabilities would be to suppress acoustic reflections or to make them smaller. And that tells you that if you want, for example, if you can cancel this wave here or make it smaller, probably you will be able to stabilize your burner. And this method has worked for a long time. This is what everyone has been doing in industry and in the lab for a long, long time. And in most cases, it worked. Let me give you one example here, which is a computation. In a computation, if you have characteristic boundary condition, it's quite easy, actually, to master the reflection of acoustic waves on the boundaries. So we did, for example, this chamber here, which is another industrial power turbine. And here you see the flow coming from the left. You inject methane by 6 holes here, and the chamber is here. It's a swirl flow. And again, you recognize that these guys of industry are not afraid of complex geometry, okay? This is not a simple one to compute. When you do that, you do simulation of this engine with reflections at the outlet and at the inlet, you see this thing is really working like a pulse combustor. Here you recognize the jets of methane which are pulsating. You inject, and then you burn. And you inject, and then you burn. Really, it's something you don't want to do in a real engine, okay? It's too unsteady. Now, if you just change the outlet conditions here, make them non-reflecting, then it gets completely stable. So that's a good suggestion that a good way to mitigate these problems is to increase the damping. Whatever the acoustic waves do, they should not come back. And so the community everywhere, industry like academic community has been thinking along that line. Now, 2 years ago, or less than that actually, TU Munich and TU Eindhoven came out with papers submitted to Combustion Flame and the Symposium, I guess, saying that they revisited theory, the basic theory of thermoacoustics, and that we probably forgot something. That probably a lot of people forgot something for 50 years now because they said there's another solution to this problem. You can have an unstable mode in a fully anechoic chamber, like this one, with no reflection at all here and no reflection at all here. And you will have an unstable mode. And that was the result of the DNS, actually. It's a DNS because it's a simple Bunsen flame. So when the paper was submitted, a lot of people got angry, saying, it cannot be right. I mean, we should know it. It's really surprising. In Toulouse, what we did was actually we repeated the simulation of Munich, almost, and we found the same thing. So we said, they may be right, actually. And so today, after many discussions, I think people understand this problem. And we think that the mechanism is actually rather simple. What you have is that if you have a chamber like this one, you can have unsteady combustion here in the chamber. And right away, you can have a wave propagating upstream. And this wave will hit the place where the flame is stabilized, create a new vortex, and this loop will turn here without ever touching the outlet or the inlet, so that you don't need reflection at the outlet or at the inlet to have a problem like this, okay? And actually, TU Eindhoven even did an experiment. That's very difficult to do in an experiment because you need to do anechoic inlet and outlet. You can see the horn they installed here on their system at the inlet. At the outlet, it's very difficult to be anechoic while you have, hot gases going out. But again, even experimentally, they proved that you can have these intrinsic modes. So why did I mention that? Well, because in industry, real engines, we have quite a few modes over the last, 20 years, which do not seem to react the way we would expect them. We increase the damping, the acoustic damping, but the mode is not damped. So that's probably because they are intrinsic. Okay? And there's a paper actually tomorrow again, and I encourage you to take a look at this one. Just one more comment about that. When these intrinsic modes were found, they were not found by doing DNS or doing experiments. They were found because someone revisited the theory. And probably the comparison is exaggerated, but if you think about fundamental physics, this is the way it works in physics. There's some theoreticians saying, my computations, my idea is that there should be a particle that you should find if you do this. And then people doing experiments look at it. It's the same here. We started looking at these modes because people revisited theory. And again, the message is the same. We need theoreticians. And that's a message for the young people in the room. Okay, so I will conclude now by saying that combustion instabilities, I hope, have proved they are a major risk in real engines. They are not only a curious animal for research. And today we have a problem because we have a hard time predicting them. It's a fascinating field of investigation, again, for the young people in this room, because we need to combine everything: kinetics, unsteady flows, hydrodynamics, acoustics, heat transfer. Now, the LUS revolution has been very strong in that field, but we should not believe that having an LES, which allows us to look at the flow field, gives us the solution to all problems. We still need experiments, and we need experiments which are targeted to look like the real engine. It's doable. You've seen the Cambridge experiment and the EM2C experiment. And also, of course, I hope I've convinced you that we need more theoreticians looking at the problem. And on that, I will conclude and thank you for your attention.
So, say it again. It's a real comprehensive tour de force on the issues of instabilities in practical combustion systems, but also on the role of simulations and combined roles of simulation theory and experiments in shedding light on these issues. We won't have time for questions, but Thierry is going to be around through the week, and I'm sure he'll be happy to entertain questions. So please join with me again in thanking him for a very entertaining talk. We would also like to congratulate him on the award of the gold medal, which is obviously highly deserved. So congratulations and well done. And we have a small award certificate here.